Welcome to our comprehensive guide on alternating current or AC for Class 12 Physics. In this video, we'll break down the fundamental concepts of AC, how it differs from direct current, and why it's so important in our daily lives. We'll start by understanding what alternating current actually means, and then move on to its characteristics, uses, and mathematical representation. By the end of this video, you'll have a solid grasp of AC and be ready to tackle any related problems in your exams. Let's dive in and explore the fascinating world of alternating current together. Alternating current, commonly known as AC, is a type of electric current in which the direction of flow of electrons reverses periodically. Unlike direct current, where the flow is steady and in one direction, AC changes its direction and magnitude continuously with time. This property makes AC extremely useful for transmitting electricity over long distances, as it can be easily transformed to higher or lower voltages. Most of the electricity supplied to homes and industries is in the form of AC. Let's look at how this current behaves and why it's preferred in power distribution. Truly understand alternating current, it's important to compare it with direct current or DC. In DC, electrons flow in a single, constant direction, which is typical of batteries. In contrast, AC's direction and magnitude vary with time, usually in a sinusoidal pattern. This difference allows AC to be easily transformed to different voltages using transformers, making it ideal for large-scale power transmission. DC, on the other hand, is more suitable for small electronic devices. Knowing the distinction between AC and DC helps in understanding why our power grids rely on alternating current. Most common waveform of alternating current is the sine wave. This means that the current varies smoothly and periodically, following a mathematical sine function. The sine wave is important because it allows for efficient energy transfer and is easy to generate with rotating machines like alternators. The smooth oscillation between positive and negative values is what makes AC so versatile for different applications. Let's visualize the sine wave and see how it represents the changing nature of alternating current. Alternating current can be mathematically represented as IT equals I0 sin omega plus phi, where is the instantaneous current, I0 is the maximum or peak current, omega is the angular frequency, t is time, and phi is the phase angle. This equation describes how the current changes with time in a sinusoidal manner. Understanding this formula is crucial for solving AC circuit problems, as it helps predict the current at any given moment. We'll use this equation throughout our study of AC circuits. AC, two important values are the peak value and the root mean square RMS value. The peak value I0 is the maximum current reached during a cycle. The RMS value, on the other hand, is a kind of average that gives the equivalent value of DC current that would produce the same heating effect. For a sine wave, the RMS value is I0 divided by the square root of 2. These values are essential for calculating power and understanding the effectiveness of AC in practical circuits. Frequency and time period are key characteristics of alternating current. Frequency, measured in Hz Hz, tells us how many cycles occur per second. The time period is the duration of one complete cycle. For example, in India, the standard frequency of AC supply to homes is 50 Hz, meaning the current completes 50 cycles every second. Understanding these terms helps in analyzing AC circuits and predicting their behavior in different applications. Phase refers to the position of a point in time on a waveform cycle. When comparing two AC signals, the phase difference tells us how much one wave leads or lags behind another. This concept is crucial in AC circuits, especially when dealing with multiple sources or loads. Phase differences can affect how currents and voltages add up, impacting the overall performance of electrical systems. Let's explore how phase and phase difference play a role in real-world AC applications. Alternating current is typically generated using devices called alternators. These machines work on the principle of electromagnetic induction, where a coil rotates in a magnetic field, inducing a current that changes direction with each rotation. This process naturally produces a sinusoidal AC waveform. Power plants use large alternators to generate the electricity that powers our homes and industries. Understanding how AC is generated helps us appreciate the engineering behind our electrical infrastructure. One of the biggest advantages of AC is that its voltage can be easily increased or decreased using transformers. Transformers work on the principle of electromagnetic induction and are essential for efficient power transmission. High voltages are used to transmit electricity over long distances, reducing energy loss, and then step down for safe use in homes. This flexibility is a key reason why AC is the standard for power distribution worldwide. Alternating current is all around us. From the lights in our homes to the appliances we use every day, AC powers most of our modern conveniences. It's used in everything from refrigerators and air conditioners to televisions and computers. The ability to easily convert AC to different voltages and its efficiency in transmission make it the backbone of our electrical systems. Recognizing where AC is used helps us understand its significance in our daily routine. Now let's look at how alternating current behaves in different types of circuits. AC circuits can include resistors, inductors, and capacitors, each affecting the current and voltage in unique ways. The analysis of AC circuits involves understanding concepts like impedance, reactance, and phase relationships. These ideas are fundamental for solving problems and designing electrical systems that use AC. We'll break down each component and see how they interact in an AC environment. A purely resistive AC circuit, the current and voltage are always in phase, meaning they reach their maximum and minimum values at the same time. The resistor simply opposes the flow of current, and the relationship between voltage and current follows Ohm's law just like in DC circuits. However, because the current changes direction, the power delivered to the resistor also varies with time. Let's see how this looks on a graph and what it means for energy consumption. When an inductor is connected to an AC source, the current lags behind the voltage by 90 degrees. This is because inductors resist changes in current, storing energy in a magnetic field. In a pure inductive circuit, no real power is consumed. Instead, energy is ultimately stored and released by the inductor. Understanding this phase relationship is crucial for analyzing more complex AC circuits that include inductors. A purely capacitive AC circuit, the current leads the voltage by 90 degrees. Capacitors store energy in an electric field and resist changes in voltage. Like inductors, capacitors do not consume real power in an ideal scenario. Instead, they store and release energy during each cycle. This unique phase relationship is important when analyzing circuits with capacitive elements, especially in combination with resistors and inductors. Impedance is the total opposition that a circuit offers to the flow of alternating current. It combines resistance, inductive reactance, and capacitive reactance into a single value, usually represented as Z. Impedance determines how much current will flow for a given voltage in an AC circuit. Understanding impedance is key to analyzing and designing AC circuits, as it affects both the magnitude and phase of the current. Resonance occurs in an AC circuit when the inductive reactance and capacitive reactance are equal in magnitude but opposite in phase. At resonance, the circuit's impedance is minimized, and the current reaches its maximum value. This phenomenon is widely used in radio, television, and other communication systems to select specific frequencies. Understanding resonance helps in designing circuits that can filter or amplify certain signals. Calculating power in AC circuits is a bit more complex than in DC circuits. There are three types of power to consider: instantaneous power, average power, and apparent power. The average power delivered to a load depends on the phase difference between current and voltage. The concept of power factor comes into play here, indicating how effectively the circuit converts electrical energy into useful work. Let's break down each type of power and see how they relate. Power factor is a measure of how effectively electrical power is converted into useful work output. It is defined as the cosine of the phase angle between the current and voltage. A power factor of 1 means all the power is being used effectively, while a lower power factor indicates inefficiency. Improving the power factor is important in industrial settings to reduce energy losses and avoid penalties from power companies. LCR series circuit contains a resistor, inductor L, and capacitor C, all connected in series to an AC source. The behavior of the circuit depends on the values of R, L, and C, as well as the frequency of the AC supply. The total impedance is calculated using all three components, and the phase relationship between current and voltage can vary widely. LCR circuits are fundamental in tuning and filtering application. In an LCR parallel circuit, the resistor, inductor, and capacitor are connected in parallel across an AC source. The current through each branch is different, and the total current is the vector sum of the branch currents. Analyzing parallel LCR circuits requires understanding how each component responds to AC and how their combined effect influences the total current and impedance. Measuring alternating current and voltage requires special instruments. AC ammeters and voltmeters are designed to measure the effective or RMS values of current and voltage. These meters are calibrated to give accurate readings for sinusoidal AC signals. Understanding how to use these instruments is essential for practical work in laboratories and electrical maintenance. Wiring in our homes is designed to safely distribute AC power to various appliances and outlets. It includes safety features like circuit breakers and fuses to protect against overloads and short circuits. Proper wiring ensures that electricity is delivered efficiently and safely throughout the house. Understanding household wiring helps in appreciating the importance of electrical safety and maintenance. Three-phase AC supply is commonly used in industries and for heavy electrical loads. It consists of 3 alternating currents, each out of phase with the others by 120 degrees. This arrangement provides a constant power supply and is more efficient for running large motors and machinery. Understanding three-phase systems is important for anyone interested in electrical engineering or industrial application. Alternating current offers several advantages over direct current. It can be easily transformed to different voltages, transmitted over long distances with minimal loss, and is compatible with a wide range of devices and appliances. These benefits make AC the preferred choice for power distribution worldwide. Let's summarize why AC is so widely used and how it has shaped modern society. Despite its many advantages, AC also has some drawbacks. It can be more dangerous than DC at the same voltage due to its changing nature, and certain sensitive electronic devices require DC power, necessitating conversion. Additionally, AC can cause electromagnetic interference in nearby devices. Understanding these limitations helps in making informed decisions about when and where to use AC or DC. Any electronic devices require direct current to operate, so AC from the main supply must be converted to DC. This process is called rectification and is done using devices called rectifiers. Rectifiers use diodes to allow current to flow in only one direction, effectively converting AC to DC. Understanding rectification is important for anyone interested in electronics or electrical engineering. Rectifiers are electronic devices that convert alternating current to direct current. There are different types of rectifiers, such as half-wave and full-wave rectifiers. Half-wave rectifiers allow only one half of the AC cycle to pass, while full-wave rectifiers use both halves. These devices are essential in power supplies for electronic gadgets, ensuring they receive the correct type of current. After rectification, the output is not pure DC but contains ripples. Filters are used to smooth out these ripples and provide a steady DC output. Common filters include capacitors and inductors, which store and release energy to even out the voltage. Filters are crucial in power supplies for sensitive electronic devices, ensuring reliable and stable operation. Working with alternating current requires strict safety precautions. Always ensure that circuits are properly insulated and grounded to prevent electric shocks. Use circuit breakers and fuses to protect against overloads. Never handle electrical equipment with wet hands or in damp conditions. Following these safety measures is essential to prevent accidents and injuries when dealing with AC. Earthing or grounding is a critical safety feature in AC systems. It provides a path for excess current to flow safely into the ground in case of a fault, preventing electric shocks and equipment damage. Proper earthing is required by electrical codes and is essential for the safe operation of household and industrial electrical systems. Fuses and circuit breakers are protective devices used in AC circuits to prevent damage from overloads or short circuits. A fuse contains a thin wire that melts when too much current flows, breaking the circuit. Circuit breakers automatically trip and disconnect the circuit when they detect a fault. These devices are essential for electrical safety in homes and industries. Transmission lines carry AC electricity from power plants to homes and businesses. High-voltage lines reduce energy loss during transmission, and transformers step down the voltage for safe use. The design and maintenance of transmission lines are crucial for reliable power delivery. Understanding how electricity travels from generation to consumption helps us appreciate the complexity of our power grid. Even with high-voltage transmission, some energy is lost as heat due to resistance in the wires. These losses are called transmission losses. Engineers work to minimize these losses by using efficient materials and designs. Understanding transmission losses is important for improving the efficiency and sustainability of our electrical systems. Industries rely heavily on alternating current for running heavy machinery, lighting, and other operations. AC motors are widely used because they are robust, efficient, and easy to control. Three-phase AC systems provide the constant power needed for industrial processes. Understanding the role of AC in industry highlights its importance in economic development and technological progress. AC motors convert electrical energy into mechanical energy and are the workhorses of industry. There are different types of AC motors, such as induction motors and synchronous motors, each suited for specific applications. These motors are preferred for their durability, efficiency, and ability to operate at different speeds. Learning about AC motors is essential for understanding modern manufacturing and automation. AC generators, also known as alternators, are devices that produce alternating current by rotating a coil within a magnetic field. These generators are used in power plants to supply electricity to the grid. The design and operation of AC generators are fundamental topics in electrical engineering, and they play a key role in our energy infrastructure. Alternating current is increasingly used in transportation systems, such as electric trains and trams. AC traction systems are more efficient and easier to maintain than their DC counterparts. They allow for higher speeds and smoother operation, making them ideal for modern public transport networks. Understanding AC's role in transportation shows its versatility beyond just homes and industry. Renewable energy sources like wind and hydroelectric power often generate electricity in the form of AC. These sources are integrated into the power grid using AC transmission, making it easier to distribute clean energy. Understanding how AC is used in renewable energy helps us appreciate its role in building a sustainable future. Alternating current is also used in communication systems, such as radio and television broadcasting. AC signals are modulated to carry information over long distances. Understanding how AC is used in communication helps us see its impact on modern technology and connectivity. Many medical devices, such as X-ray machines and MRI scanners, operate using alternating current. AC allows for precise control of voltage and current, which is essential for the safe and effective operation of sensitive medical equipment. Understanding AC's role in healthcare highlights its importance in saving lives and improving well-being. Most lighting systems, from incandescent bulbs to modern LED lights, are powered by alternating current. AC allows for efficient distribution and control of lighting in homes, offices, and public spaces. Understanding how AC powers lighting systems helps us appreciate the convenience and comfort it brings to our lives. The future of alternating current technology is bright, with ongoing advancements in smart grids, renewable integration, and energy efficiency. Innovations in AC systems are making electricity safer, more reliable, and more sustainable. Staying informed about these developments helps us prepare for the evolving landscape of electrical technology. Let's recap what we've learned about alternating current. We covered the basics of AC, its mathematical representation, and its behavior in different circuits. We explored its advantages, applications, and safety measures. Understanding AC is essential for anyone studying physics or pursuing a career in engineering. With this knowledge, you're well equipped to tackle AC-related questions and challenges. Congratulations on completing this comprehensive guide to alternating current for Class 12. We hope you now have a clear understanding of AC's principles, applications, and importance. Keep practicing problems and exploring real-world examples to deepen your understanding. Stay curious and continue your journey in the fascinating world of physics and electrical engineering.